Today, we're in the woods of North Carolina to talk about black holes, obviously. Now, specifically, we're going to be talking about a black hole called M87 star and the story behind what it took to actually get this image right here. This image is the first image ever taken of a supermassive black hole. Getting this image was actually a remarkable challenge, and that's part of what makes this story so interesting to tell. Why was it a remarkable challenge? Well, black holes, though they are incredibly massive, they're also incredibly small. They are infinitely dense, and so it's very hard to find them in space, let alone take images of them. In this case, this supermassive black hole, M87 star, is at the center of a galaxy called M87. This galaxy is 53 million light years away from Earth. If you're trying to image something in astronomy, it helps for it to be large, close to you, and incredibly bright. Black holes are none of those things. They're small, often very distant, and don't emit visible light in the way that our eyes would typically perceive them. In fact, in order to take this image of M87 star, we needed to observe it in microwaves. And in order to observe it in microwaves and get any sort of clarity like you see in this image, we had to get clever. Part of the challenge is that when trying to image a black hole, we want clarity, right? We don't want just a fuzzy blob of light. We want something where we can see the ring structure of the accretion disk. This is actually exceedingly difficult to achieve because of those reasons I was just talking about. In order to image something that's so small and so far away, you need a massive light collecting area in order to get a complete image. In fact, in the case of M87 star, we wanted an image where we could see that accretion disk, and we did the calculations. In order to achieve that goal of getting an image where we can see the accretion disk, we would need a telescope the size of the Earth. That is the light collecting area that we would need. That's obviously quite a design challenge. That's very, very difficult to achieve, if not completely impossible. It is completely impossible. But as we know, scientists are very clever. They like to come up with creative ways to fix very big problems. Now, in this case, the very big problem is we need a telescope larger than the planet that we live on. That obviously can't happen. But we do have radio telescopes located all across the world, scattered across all hemispheres. What we can do then is we can link together the data from all of these telescopes to create a telescope that's as large as the Earth. Now, this is a technique called very long baseline interferometry, and that's a mouthful, but it's the technique where we're linking together those telescopes, linking together all of that data in order to tell a complete story. Now, this is a task that we were actually able to accomplish. It's something called the Event Horizon Telescope, named after the event horizon of the black holes that we're trying to observe. It was an international project linking together telescopes from all across the world. In fact, it's 8 telescopes. Okay. In fact, it's 8 telescopes located in a variety of different countries. We have some in the US, some in Chile, some in France, some in Spain, and when we link them all together, we create a complete radio telescope that's the size of the entire Earth. Now, as a bit of a tangent, one of my favorites is actually at the South Pole. We have a radio telescope, or more precisely, this tree's gonna fall any second. Okay, so we have 8 telescopes located all across the globe. One of them is actually on the South Pole. It's called the South Pole Telescope. It's observing microwaves from the cosmic microwave background. As a bit of a tangent, if anybody wants to take me to the South Pole Telescope, please let me know. If you have an extra ticket, whatever, I don't know how it works, please take me to the South Pole Telescope. I want to go look at it so bad. Please, I want to go to the Amundsen Scott Research Base on the South Pole and look at space. Thank you very much. Okay, so what does this all mean, right? We've talked about M87 star, we've talked about the first image ever taken of a black hole, but what even are black holes? They're kind of these abstract objects that people vaguely fear but don't really understand, like a lot of things. People think that black holes suck everything in. When they hear that there's a black hole at the center of our own galaxy, they think, oh gosh, how far away is Earth? Are we in danger? Well, no, black holes don't suck. They're gravitating bodies just like anything else. They're just super, super dense. This is part of what makes black holes so magical. They are some of the most fundamental macroscopic objects in the entire universe. Here's what I mean. The black holes of nature are the most perfect macroscopic objects there are in the universe. The only elements of their construction are our concepts of space and time. Now, I didn't write that. Do you think I can write like that? That's what Chandrasekhar, a famous astrophysicist, said in his 1983 book, The Mathematical Theory of Black Holes. Now, Chandrasekhar was an absolute legend. He earned the Nobel Prize in Physics in 1983 for just being a legend. He revolutionized our understanding of stellar evolution and stellar structure. He was amazing. Okay, so why did Chandrasekhar say this? Why did he say that black holes are the most perfect macroscopic objects? That is what we are going to explore next. And in order to do so, we have to explore where black holes actually come from. And it's going to be quite the story. So what even are black holes and what makes them perfect? Well, this is what we're going to explore next. In order to understand what makes black holes the most perfect macroscopic objects in the universe, we need to understand where black holes come from in the first place. Once we understand where black holes come from, we'll understand the elements of their construction and what makes them perfect, simple, fundamental macroscopic objects. So the origin of black holes is closely related to the origin of stars. In some sense, stars are the most important structures in the universe. They're some of the first structures to come to be in the beginning of the universe, and they are what make up the centers of solar systems and the mass of galaxies. And if we are to understand the origin of black holes, we must first understand the origin of stars. In the beginning of the universe, there was mostly hydrogen and helium. That's what the Big Bang blessed us with. So there were large pockets, large clouds of gas and dust in the early universe that came to be. They coalesced together thanks to gravity, and they began to form stars. When you have a large cloud of gas and dust that collapses in on itself due to gravity, eventually it'll heat up and spin to the extent that nuclear fusion starts in its core. Nuclear fusion is the engine of a star. It is what keeps the heat going. Essentially, what the inside of a star is doing is it's taking smaller elements and building them up into larger ones. It's real-life alchemy. What it's doing is it's taking smaller elements like hydrogen and helium and colliding them together until you can create heavier elements like boron, carbon, and all the way up to iron. Iron is where fusion stops in stars. Stars cannot produce elements heavier than iron because it takes more energy to produce iron than the star gets out of it. It's essentially a loss. What this means is that once the star runs out of fuel, that is to say, once a star burns everything that it has and it can't produce anything heavier than iron, it essentially dies. Now, this looks different for different sizes of stars. So what we're going to be focusing on today are massive stars. These are stars that are orders of magnitude larger than our sun. These are absolutely ginormous stars. These are absolutely ginormous stars. They are dominated by gravity. So what happens when they run out of fuel is very interesting. Essentially, they puff out their outer layers, let go of that extra gas, and they turn into what's called a red supergiant. But because gravity dominates in these massive star systems, they collapse back in on themselves and then explode in what's known as a supernova. Now, supernova are kind of confusing. Astrophysicists don't understand them entirely yet. What we do know is that supernovae are where heavier elements than iron largely come from. So any gold or silver or anything heavier than iron is produced in dying massive stars. This blows away a lot of the gas in the system, but it doesn't get rid of everything. What's left behind at the center is the supernova remnant. This is either a neutron star or, in some special cases, a black hole. Now you might be wondering what determines whether or not a neutron star or a black hole is left behind. That's something we don't entirely understand yet. We think that it has something to do with mass, but it could have a variety of different factors involved. Stellar mass black holes are left behind by those supernovae, those dying massive stars, and that is where black holes come from. Now, the supermassive black holes that are at the centers of galaxies, those are a different story. Those come together, we believe, thanks to the combination of those stellar mass black holes. However, that's something that's still actively being researched. Okay, so now that my fire is a little bit less ugly and I have a sufficient amount of tar in my lungs, we can keep talking about black holes. As I mentioned, black holes come from stars. when a star dies, a black hole is left behind. And this is where we believe that those supermassive black holes at the centers of galaxies come from. We believe that those are just collections, mergers of smaller stellar mass black holes. When that star dies, what's left behind at the center, the core, collapses into infinite density. This is the singularity of the black hole. This is what's at the very, very center. So Einstein described the universe through 4 dimensions. He talked about space, x, y, z, and then time, t. And those are the coordinates of space-time. That makes up the fabric of reality. Essentially, when a star goes supernova and it expands into the red giant phase, collapses, and then explodes, when it leaves behind that black hole, it leaves behind something that is infinitely dense. The center of that black hole, the singularity, tears a hole in space-time. That hole in space-time leads to some weird things, but more importantly, that simplicity, the relative simplicity of the singularity of the black hole, just something that's infinitely dense, is what makes black holes the most perfect macroscopic objects. This is something called the no-hair theorem. Don't ask why it's called that, I have no idea. The no-hair theorem says that black holes can be completely described using only 3 things. That is mass, electric charge, and angular momentum. So how much mass is there, how much electric charge is there, and then how quickly it's spinning. Those 3 things are what make up a whole black hole. Those 3 things can describe what that object actually is. Now this is in stark contrast to planets or stars, which need way more dimensions of analysis in order to understand them completely. This campfire right here is more complex than a black hole is. Did I make a campfire just for that comparison? Absolutely. This campfire here is more complicated of a system than a black hole is. Black holes are only made up of space and time. That's what Chandrasekhar meant when he said that. Though black holes are incredibly impressive and remarkably bizarre, they are remarkably simple. That's not to say that the physics and the mathematics needed to understand them is simple. It's the elements of their construction are remarkably simple. They are just pits in space-time. So now that we've uncovered what makes black holes the most perfect macroscopic objects, let's return to this image of M87 star and talk about what's actually going on here. Okay, so let's take a quick look at the anatomy of this image of M87 star. There's a lot going on here, and it all has to do with that singularity, ultimately. Okay, so when you look at that image of M87 star, you see a couple of things. First of all, you see that glowing orange donut shape. That's the accretion disk. That's essentially gas that's orbiting around the black hole, falling in and heating up as it falls in. When it heats up, it emits that light that we're observing in those microwaves. Now, we might notice that one side of this ring is brighter than the other side. That's because the black hole is spinning, or rather, the accretion disk is spinning around the black hole. The side that's orbiting towards us, the side that's coming in our direction, is going to be brighter than the side that's moving away. This is because of something called photon beaming. Essentially, the brighter side is brighter because of a traffic jam of photons. It's orbiting in our direction, so they're getting jammed up and causing a brighter image. Whereas on the side that's orbiting away from us, they're orbiting in a different direction from our observation, so they're going to be dimmer. Now let's focus on the dark spot in the center. This is what we might think is the black hole itself, right? Black holes are black because light falls in and can't come back out. But actually, the true event horizon, the true black hole itself, is about half the size of that dark spot that you see in the center there. The rest of that dark spot is what's called the event horizon shadow. The event horizon itself is where the escape speed is faster than the speed of light. Essentially, escape speed is the speed that you would need to go in order to escape the gravitational bound of a given body. Here on Earth, the escape speed is about 11 kilometers per second, but a black hole has an escape speed that is faster than the speed of light. Nothing can travel faster than the speed of light, so things fall into a black hole and can't fall out. The point at which that happens, where the escape speed is faster than light, is what's called the event horizon. That's what the Event Horizon Telescope is named after. So what does this mean as far as the big picture? Well, if things fall into black holes and can't come back out, essentially all data is lost. We can't send something in to figure out what's in there and then come back out and retrieve it. That's why black holes are so theoretical. We're truly using only math in order to uncover the secrets of these perfect macroscopic objects. So when things fall into a black hole, that data is lost forever. It's gone. It falls out of the universe, essentially. One of my favorite ways to describe this is through analogy. We've all been in our car before, and we know that crack in between the seat and the console that things fall in, and then they disappear. They're no longer in the universe. We can kind of show that here. That's exactly what black holes are like. When you look at this crack here, things go in, but then they can't come back. Oh,